Hi everyone, welcome back to part 2 of transformations of functions. So we're going to start off by talking about vertical stretching and compressing, also known as shrinking. Okay, so when you see a number out in the very front, okay, that is what's going to cause the graph to be vertically stretched or compressed. So we are going to take the absolute value of that number, and if it is greater than 1, then our graph is going to be vertically stretched, okay? Which means that every y value in the graph will be multiplied by that a value. If we take the absolute value of a and we get it to be between 0 and 1, then that is going to be vertically compressed. That means every y value will be multiplied by that a. Now, the reason I am saying the absolute value is because if we have a function that is like -2 of f of x, that negative causes a reflection, and so what's going to cause it to be vertically stretched or compressed is going to be that 2. So if we take the absolute value of -2, that would give us the 2 for this stretch. Okay, that's why I have the absolute value. If you know to ignore the negative sign for a compression or a stretch vertically, then you don't have to necessarily worry about the absolute value. So looking at our first example, we have n of x equals 2x squared. We know the parent function of this is x squared, the quadratic function. So we also know that n of x can also be written as 2 times f of x, since we made that connection to the parent function. So what that means for us in this problem right here is that every single x value is going to be multiplied by 2, every single y value is going to be multiplied by 2 from the parent function. So if my parent function has these following points, 0, 0, 1, 1, 2, 4, and then if I look on the other side, I have -1, 1, and -2, 2. So what I'm going to do is I am going to take those x values, those y values, and I am going to multiply them by 2. So I'm going to highlight all of the y values that we're going to multiply by 2. So 0 times 2 is going to stay 0, so that stays the same point. But here, 2 times 1 is 2, so my new point is going to be 1, 2. Same thing happens over here with -1, 1. We take that 1, we multiply by 2, we get -1, 2. Then I have 2, 4. If I take that 4 multiplied by 2, I get 8, so it would be 2, 8, which is off of my graph, but let's just guesstimate that it's somewhere up here. Same thing for that. I don't want to mess up my writing that I have, so I'm going to not do that. But just so you know that we would have points off the graph. So we connect the dots. See if I can connect them a little better. Looks something like this, okay? So this would be our transformed function right here with a vertical stretch because it was bigger than 1 of 2. Okay, looking at this next one, we have p of x equals 1/2 x squared. We have our parent function to be x squared. Okay, so p of x can be rewritten as 1/2 f of x. Okay, just so you know, those are the same thing. This would be because 1/2 is between 0 and 1. This is a vertical compression. Of 1/2. So I am going to take all of those y values that we started with in that original one, and now we're going to multiply them by 1/2. So 0, 0 is going to stay the same. If I take that y value of 1, I multiply it by 1/2. Now I have 1, 1/2, which would be about right here. So I would also have -1, 1/2. if I take the y value of 4 and multiply it by 1/2, I get 2. So I would have 2, 2, and negative 2, 2. Okay, so then I just connect all my points. Oops. And I make it look as best as possible, sorry. There we go. I get this graph right here. So what I want you to notice is that with a vertical stretch, okay, I'm essentially pulling the graph up and down so it's getting skinnier. When I'm doing a vertical compression, I am squishing the graph in towards that x-axis and it gets wider. Okay, so when I'm stretching it, I'm pulling it up and down. When I'm compressing it, I'm pushing it together. Okay, so that's the difference between a stretch and a compression when it comes to a graph. Now we're going to talk about a horizontal stretch and compression. Okay, so this is when the value is inside with the x. So if that b value is greater than 1, it is going to be horizontally compressed. Now this time, every x value is going to be divided by b. So now we're messing with the x values. Okay, if it's between 0 and 1, this is a horizontal compression, a horizontal stretch, and every y value again is going to be divided by b. So I look here, I have q of x equals the absolute value of 2x. I know that my parent function is the absolute value of x. So q of x could also be rewritten as f of 2x. Because it is greater than 1, okay, the 2 is greater than 1, that means it's going to be horizontally compressed. Okay, so for a horizontal compression, I am going to take the x values and I am going to divide them by 2. Divide them by 2. Okay, so I have the following x values. I have 0, 0 for that point. This point right here would be 1, 1. 2, 2. And then I'm going to jump to 4, 4. And I have the same points but negative values over here. So negative 4, 4. This would be negative 2, 2. And this right here would be negative 1, 1. So I'm going to divide each x value by 2. Each x value by 2. So 0 divided by 2 is going to stay. So I have 0, 0. 1 divided by 2 is 1/2. So I have 1/2, 1. And negative 1/2, 1. 2 divided by 2 is 1. So I have 1, 2. And negative 1, 2. 4 divided by 2 is 2. So I have 2, 4. And negative 2, 4. So my function, should look like this. Okay, so notice when I have a horizontal compression, we are squishing it towards the y-axis. We're pushing it together towards the y-axis. Okay, it looks very similar to a vertical stretch, but they are different. So don't get them confused, okay? The x values would not be the same. Now, looking at this one, we have r of x equals the absolute value of 1/2 x. So our parent function is the absolute value of x. So r of x can be rewritten as the absolute value of 1/2 x. Oops, sorry, that's the same thing. It would be the f of 1/2 x. There we go. Okay. So this is a horizontal stretch. Okay, so we're going to take each x value, and we are going to divide it by 1/2. Divide it by 1/2. So 0, 0 is going to stay the same. If I take 1 and I divide it by 1/2, so just so you can see what happens, 1 divided by 1/2. Well, when you're dividing by a fraction, we learned a long time ago that we can multiply by the reciprocal. So 1 times the reciprocal of 1/2 is 2 over 1, which is 2. So I have the point 2, 1, and negative 2, 1. Then if I take the next x value of 2 and divide it by 1/2, that is the same thing as saying 2 times the reciprocal, which is 2 over 1, which would be 4. So I now have 4, 2, and negative 4, 2. Okay, if we did 4 divided by 1/2, that would be the same as 4 times the reciprocal of 2 over 1, which would be 8, and I don't have enough space to graph that. Okay, so I connect my dots. Oops. So it looks something like this. Okay, so notice that when it's a horizontal stretch, we pull it away from the y-axis. Okay, we're pulling it away, so it's looking like a vertical compression, but again, this is a horizontal stretch. Okay, so now what happens when we have multiple transformations? Well, we need to make sure that we do these in the proper order so we avoid any error. So the order in which I suggest is starting with a stretch or compression first, okay, whether it's vertical or horizontal, then go to reflecting, and then the next part, it kind of just depends on your preference. You can do a horizontal shift and then a vertical shift, or you could do vertical then horizontal. Okay, these can be done in the same step. Okay, this one, it doesn't matter, they are the same. Not the same, but it doesn't matter the order in which you do them in. Okay, so we have example number 7. Identify the transformations and graph the function. Well, first off, we want to identify if there's a stretch or compression. I notice that there is a 2 out in front. So that tells me since it's out in front, it's vertical. It's bigger than 1, so it's a vertical stretch. Okay, notice how I just focused on the number and not the negative sign. Because that negative sign right there, since it's out in front, tells me it's a reflection. And since it's out in front, it's over the x-axis. If it was inside with this x right here, it would be over the y-axis. Then I see that there is a +3. So since it's on the inside, I know it's acting opposite. So this is going to the left 3. And then I notice that there is a -1. And that tells me that it is going down 1. Okay, so here we go. We're going to start with vertical stretching. So I'm going to do one transformation at a time. So with a vertical stretch, remember that I am changing the y values. So I get 0, 0. Instead of 1, 1, it's going to be 1, 2. 1, 2. Instead of 2, 4, it would be 2, 8, which is off my graph. So I am just going to connect what I have here. See if I can make it a little better. There we go. Okay, so the red is only representing the vertical stretch, so 2 times the f of x. Now what we're going to do is we're going to do a reflection over the x-axis, which means each of my y values are going to change to the negative version. So if this is 1, 2, or -1, 2, and this is +1, 2, each of those y values are changing to the negative version. So I'm still going to have 0, 0. And instead of -1, +2, it's going to be -1, -2. Instead of 1, 2, it's going to be 1, -2. And so now I have the reflection. So this purple graph is representing the reflection and the vertical stretch. Now I am going to worry about moving my graph to the left 3. So I'm going to take each point and I'm going to move it to the left 3 spaces. And that's where its new point is at. So I have this point right here. I move it over 3 spaces. So I have a new point there. I have this point here. I move it over 3 spaces. So I'm going to have a new point right here. Okay, so that right there represents me moving the graph to the left 3 spaces. So this would be -2 f of x plus 3. Now for the final graph, I'm going to do it on this nice pretty clean one so it's not too confusing, but I am going to talk about it as we go through. So all we're doing now is we're moving each point down 1. Each point down 1. Okay, so instead of being at -3, 0, it's going to be at -3, -1. Instead of being at -2, -2, it's going to be at -2, -3. And instead of being at -4, -2, it's going to be at -4, -3. So now I have my final graph right here. So this represents f of x. So it's -2 f of x plus 3 minus 1. So that is the whole entire transformed function. Okay, so again, notice how I did it I took one transformation at a time rather than trying to do them all at the same time. So if you have any questions, please make sure you write them down and you ask your teacher the next time you see them. And I'll see you in the next video.